Hello, this is the capacity estimation lecture in the air traffic management course DNFL 10 taught in Linköping University. And I'm Valentin. I will be giving this lecture. So I will speak about our evolution of understanding of what capacity estimation in ATM is. And here is the setting. We have, well, the airspace, in this case, the airspace over the US. And maybe something interesting is happening, somewhere around here, and some flow constraint area, or there is some weather event. Well, here is the zoom in on the area. So, well, yeah, there are some weather obstacles, and some flights have to go from left to right. And the air traffic managers want to know how much flow can you route from left to right in this area. So what is the capacity of this airspace? And the flows is measured in the number of the air lanes that you can route through. So an air lane is modeled by a thick path. So there is some central line of the path, and then the path has some thickness, and this thickness represents something that called the required navigation performance, or RNP. So RNP is the parameter. It's the width, let's say 1 nautical mile, or maybe up to 5 nautical miles, and the aircraft, due to navigational errors, due to winds and other things, cannot follow the center line precisely. So it may be somewhere, around this center line, and the width within which the aircraft stays 95% of the time is called the RNP. So we can think of this RNP as the width representing the thickness of the path. So we want the paths to be thick, the paths for different aircraft to be thick and well separated. I will give some pictures. In fact, here is a picture that I took on E4 when going down to Malmö. You can see how the aircraft fly through the sky, and how they go, in parallel. So one aircraft, another aircraft, another aircraft, and they stay separated. So there is some distance between these air lanes. Well, sometimes the distance is larger, but they go kind of on these parallel tracks, and we want to fit these tracks through a possibly weather impacted airspace. So here is how we model the problem. We have our airspace, which I will be representing just by a rectangle, or in this case, a square. So this is our airspace. It can be an air traffic control center, a sector, or some flow constrained area. It doesn't matter which particular airspace it is. And some parts of the airspace are blocked. They may be blocked by hazardous weather systems, by the so-called special use airspaces through which the flow is forbidden. It doesn't matter. There are some no-fly zones. So these red obstacles will represent the no-fly zones for the aircraft. And the question in the capacity estimation is, how many air lanes can we fit through this airspace going from left to right? So this left side of the airspace is the source through which the flow comes in. The right side is the sink through which the flow comes out. And we want to route air lanes from left to right. And then every air lane has a thickness, as we discussed. So it's a path with a certain thickness. And then we assume that the aircraft would just, flow one another like ducks in a row along each of the air lanes. So the question is not really how many aircraft we can route through, but how many air lanes. And then through the air lanes, we would route the aircraft one after another. So some of the assumptions, of simplifying assumptions that we have in this model, we consider en route airspace. As you heard in the previous lectures, well, the aircraft in most cases, or at least long haul aircraft, spend most of their time en route. So that's quite an important part of the flight. So we look at a single flight level. So we do not consider the three-dimensional problem. We just have a plane, x, y. The problem is static. We don't consider the time component. So we assume that these obstacles are static and everything is static. Maybe we are considering, short time horizon when the weather systems don't move, or maybe these obstacles represent some special use airspaces like military airspaces, some other no-fly zones. And yes, we're only considering flow going in one direction, in this case, from west to east. So we don't consider the crossing flow, which could go like this. And partially, this last assumption is justified by the so-called alternating altitude rules when the air traffic going in different directions is kept altitude separated. So, like even flight levels are going in one direction and odd flight levels going in the other direction, so that if the flows have significantly different headings, then they're kept altitude separated. And if we look at an airspace at a single flight level, it's really a two-dimensional airspace, and the traffic flow is mostly unidirectional. Okay. So one obvious observation is that the capacity of the airspace is somehow related to weather coverage. So if the airspace is fully covered with hazardous weather systems like it is here, then, well, the capacity is probably small or zero. And if there is no weather, then the capacity is large. You can route lots and lots of air lanes, like over here. But you can immediately understand, come to think of it, that the capacity does not only depend on the location and the location of the weather systems and the percentage of the airspace covered with the weather. It could be that the same weather systems and hence the same weather coverage, the same percentage of airspace covered by the weather, hazardous weather, leads to completely different capacities. So in particular here on the left and on the right, I have absolutely the same obstacles, geometrically the same obstacles, the same weather systems. But on the left, well, you can route quite a few air lanes from left to right on this left picture. Well, depends on the thickness of the air lane. Maybe you can route even more. While on the right, the same obstacles, they kind of form this squall line, if you wish, if you're talking about the weather, and the capacity is zero. You cannot route any thick air lanes through this airspace on the right. So depending on how the weather systems are organized, like this popcorn convection versus a line, the same weather coverage or even the same weather systems could lead to completely different capacities. So how do we estimate the capacity of the airspace for an arbitrary set of weather obstacles inside the airspace? The ultimate answer was given by something which was called the minimum cut, or min cut, through the airspace. So what is that? So imagine that these obstacles are really the holes. So your airspace is a piece of paper, and when I was teaching in class, I would really take a piece of paper with me with some holes. So all these obstacles are holes. I would prepare the piece of paper and carve out some holes. And you have this left side, your source. This I denoted with S. And you have the sink. Well, I denoted with T. And now you're trying to cut S from T. So I would take scissors and would try to cut from bottom to top by some line so that I cut as little as possible through the paper. So these holes, they are already kind of pre-cut for me. So these are already holes. And I'm trying to find the kind of simplest or the shortest path from this bottom to this top while going through as little white as possible. So red is free. And I'm kind of doing this island hopping. So another idea how to understand this min cut, this minimum cut, this green line, is that these red are the islands, and I have to go from bottom to top. And well, I have to swim through white, and I want to swim as little as possible. And then the bottleneck, or this line, which doesn't have to be a single line, it can go from island to island, from obstacle to obstacle. Now I have too much red over here. So this green line really in this particular picture represents the minimum cut. It's kind of the bottleneck, the thinnest place in this airspace uh, through which the flow has to go. And the capacity airspace is really defined by this minimum cut. Okay, so for an arbitrary geometry of the obstacles in the airspace, you can compute, you can find this shortest cut, or minimum cut, shortest path, a minimum cut, and that minimum cut defines the capacity of the airspace. So you can route the air lanes so that they kind of saturate the minimum cut. So this minimum cut gives you the bottleneck. The air lanes have to cross the minimum cut and have to saturate it. But elsewhere in the airspace, the air lanes can wiggle in different ways. They can go like this, maybe another can go like this. So there is quite a lot of freedom. The only bottleneck, the only saturation happens along the minimum cut. Okay, so that's some kind of an answer for the problem of estimating the capacity of the airspace. There are many ways in which we can think of the weather impact on the air routes. So what we were looking at just now is this kind of no flying zones. So everything was either flyable or not flyable. Uh, Black and white 0, 1, there was no cost really related to intensity or severity. You could alternatively say that, well, going through different kinds of the weather you're going through different kinds of the weather, you incur different costs. And this is true because, well, there is some weather cells are really hazardous and nobody would fly through them. But through other weather cells, things depend. They depend on the pilot, they depend on the airline policy, depend on the aircraft. So some aircraft may go through some weather through which other aircraft would not go, but they would incur different costs, and we could think of models like that. We could say that it's okay to go through a bit of weather, but we don't want to go too much exposure over the whole path, or we should not be exposed to weather for very long, and consider various other models for the weather impact. So for this no-go constraint, if you have a weather system, you really have to go around it, maybe including certain threshold delta, which kind of specifies this clearance of the route around the weather. You could also look at the clearance in terms of the altitude, in terms of trying to fly over ecotops. So sometimes, the pilots do that, even though they're not always sure how high the weather obstacle is, so they would rather dive under the weather obstacle, but you can also clear the weather obstacle from above. But anyway, so this no-go constraint means that you really have to avoid this weather. But other kinds of models could be more realistic. And we may say, for instance, that it's okay to go through the weather every so often, but the total amount of time or the total distance spent within the weather shouldn't exceed a certain threshold, Dmax. Or alternatively, you may say, well, it's okay to travel for a bit inside the weather, like over here, but then you have to go through a clear airspace and then maybe again cut through the weather. But then again, you would have to have quite a long stretch of the airspace which is free of the weather, free of obstacles. There is still an ongoing discussion which of these models really reflect how the aircraft go through the weather. Few years back, with our air traffic controller students down in Malmo, there was a thesis where two students looked at different models of flyable paths, still not coming to the ultimate widely accepted answer of what is the right model for a flyable path. And well, a lot of researchers actually looked at how the pilots go through the weather systems. And here again, the red is the obstacles, and this light green is the nominal path. And then, yes, the circles and crosses represent how the pilots go through the weather. And well, they, as you can see, sometimes they clip through the weather. They don't really avoid it 100% of the time. And moreover, sometimes the pilots deviate from the nominal route and maybe go through the piece of the weather which is thinner than the nominal weather goes through. And sometimes they would deviate from the nominal route and for some reason go through the obstacles. It's not completely clear why and how they go through the obstacles, and we can only try to model the pilot's behavior. And in particular, we've been trying to model the paths which are not thick everywhere, but which are kind of mostly thin, represented by a thin thread. But every so often they have to be thick. So we were modeling them with these necklaces, really saying that these, well, these larger pieces of airspace, which should not contain too much weather, they should represent some wiggle room for the aircraft, so that the aircraft, well, it can go through the free airspace, and then if needed, it can go around obstacles, then again go through free airspace, and if needed, have some room to go through the free airspace and so on. So these threads of the necklaces could go through the obstacles or very close to the weather obstacles, but every so often you kind of have to have this free space, free in terms of the free of the weather. So yeah, that's another model. And we started routing these paths again from left to right, trying to estimate the capacity of the airspace. So here is a picture. So the ZOB is the Cleveland center, and these thick black lines, they represent the boundary of it's a center, Cleveland center. There are several sectors inside it, I think. And well, there's quite a lot of traffic that goes in the US, from west to east. And these blue things, they actually represent the Great Lakes. So over here on top, this Cleveland center, it's the boundary between the US here and Canada up here. So, well, so that some geography. I mean, it's real center. And these are obstacles, and the obstacles, we just generated them randomly, so they weren't real obstacles. And we were routing paths, from left to right, and each path was this kind of necklace, a thread with certain beads around the thread, which happen every so often. And we started showing it to our colleagues in the air traffic industry, and they were saying that, well, your beads are okay, but they should have triangular shape. Why triangular? Because triangles represent the so-called time stretch maneuvers. So what's the story here? Well, the aircraft may go through a center or a sector which is not weather impacted at all, and in principle you can route lots and lots of air lanes through it. But it could be the case that there is some kind of blockage, temporary blockage at the exit from the airspace. I don't know, for instance, you may think of the flow that in this case goes from, well, north to south, and you have this time separation that sometimes the flow goes like this, sometimes the flow goes from west to east. And so the aircraft that go through this airspace have to spend some time inside this airspace. And of course, one possibility is that while the aircraft go more slowly, or maybe have even ground delay, but if the aircraft are already airborne, the engine goes into a certain regime. You don't want to change the speed too much time. And what the aircraft do is that they do these time stretch maneuvers. So an aircraft, would go left and then right, return to the path, and that's a standard maneuver. It will kind of eat up some time and stretch the time. So, and doing these time stretch maneuvers would let you come to the sink a bit later, and this is what you need when the temporary blockage is gone. And of course, when you're routing the aircraft with these time stretch zones, or routing the air lanes with the time stretch zones, the stretching zones from one of the air lanes shouldn't intersect another air lane. Well, because then there could be a conflict between an aircraft doing a time stretching in this one and the aircraft flying straight in this air lane. So you want to route these necklaces with triangular beads, and these triangular beads should be disjoint from each other and from the other paths. So this is not a particularly good picture. And well, here is a couple of examples of these very specific templates for the time stretch maneuvers. So we know quite well what are the angles of these triangles, what is the length. Well, at least in Boeing, the aircraft, you just can press a button in the flight management system and saying, well, I have to do a time stretch maneuver starting at a certain waypoint, and it will kind of do it for you. So automatic or semi-automatic, a pretty standard thing. Similar thing, of course, is applied in terminal maneuvering area. So here we have the airflow merge into an airport, and you can see how the aircraft are doing quite a lot of path stretch or time stretch maneuvers, not going straight down to the airway, but really doing these wiggles to eat up some time. And yeah, these wiggles are pretty standard. Okay, so this is the output again of our algorithms. So this time we were drawing the obstacles not just as red things, but as these kind of things with some heat map. But still, they were obstacles, and we were out in paths again from left to right with the beads of triangular shape representing the path stretch maneuvers, and again trying to ask ourselves the question, how many air lanes can we route? What is the capacity of this weather impacted airspace under a certain model of what a path is? And here I'm referring to an applet which used to work as a Java applet that a student of mine did back at Helsinki. It doesn't work on my browsers, but if it works on one of your browsers, then you're almost welcome to play around with the applet. You can define your own obstacles, and you press a button and the applet routes the paths for you. Here I'm just showing it now, an output. Next thing, so of course you do the time stretching when you have to eat up a bit of time, like a couple of minutes. But again, every so often you really have to eat up a lot of time, and then you go into holding patterns. And well, here is one picture of a holding pattern of quite a few aircraft doing holding pattern. I would say in the vicinity of the airports, and this is pretty low. Here is more. You can see these traces, and here I have a link. I've been gathering myself. One day I was bad weather in 2012. I forgot what day it was. Maybe you can see somewhere here. And I was just taking screenshots of flight radar, seeing how the different aircraft, because of a lot of snow, well, had to go quite a lot in the time, in eating the time in the holding patterns. There were more, so the aircraft would wiggle for quite some time before landing. There were, all over Europe, there were these poor aircraft not getting to their destinations sometimes because it was also watching where they were destined and where they eventually were had to land. So you can really see these shapes. You can see these racetracks. Well, like over here, also the aircraft was routed somewhere else. This is in New York. Again, an aircraft had to do quite a long time stretch maneuver before it landed elsewhere. Of course, in London Heathrow, you see these stacks where the aircraft doing the time stretch maneuvers before they can land. So anyway, things like this, you should reserve parts of the airspace for these time stretch maneuvers. And if you look at the safety map analysis done by Eurocontrol, uh, they identified 5 most important safety risks. And one of them was this aircraft operating, well, they have without transponder. You can say that's, you know, an aircraft which doesn't listen to the air traffic controller. You don't know where it is. You only know where it was at some point, and then it just flies through. And the other aircraft should make sure they don't conflict with it. So should do the time stretch maneuver and so on and so forth. So there are so I'm looking at this number 1. Um, Safety risk. There are a few risks associated with the runways at the airport. And then there's this risk number 5, which is also very much related to air traffic management, at least in the way it's done today, when, as you know, we have different sectors. And well, different sectors are controlled by different controllers, and there is really a handover between the controllers when the aircraft goes from one sector to another. And it's quite important and quite risky if you know, 2 controllers, one monitors the aircraft in one sector, the other monitors in an adjacent sector, and the aircraft which are close to the boundary or between the sectors, they are actually close to one another, but the controllers don't know about that. So we will look at these 2 uh, safety risks. So, well, imagine that you have, you know, a route structure like this. Again, the green are the routes, the dashed are the sector boundaries. This is an artificial example. We didn't take it from any particular airspace, and the green represent the air lanes or the routes. And well, there are aircraft following the routes. Everything is nice. But then there is an aircraft with a dysfunctional transponder, rogue aircraft going through. And so all these aircraft that may conflict with this one have to spend some time and you know, not get to this. So it's like this temporary blockage that we looked at earlier. They have to eat up some time on along their routes. So it would be nice to have again these holding patterns or holding rooms attached to these routes. And of course, again, the holding patterns for different routes should be disjoint. So they shouldn't overlap between themselves and shouldn't overlap the other routes. And yes, also the looking back at this safety hazard of air traffic controllers not communicating over the sector boundaries, these wiggle rooms should be attached to routes within sector boundaries. So we wouldn't want to attach a wiggle room to, you know, to this route like this, because, you know, an aircraft wiggling or spending time here doing the holding pattern, it would be changing sectors back and forth. And well, every time you would really need to communicate between the controllers, because there could be another traffic in this sector. So this is a fictitious example. I will return to it also for some other questions on capacity estimation, but again, just to show you kinds of the problems that you may have when designing the routes. Uh, you have your airspace and you want to route the air lanes from left to right, but you also have to attach these holding patterns. And then, well, you may also want to put these circles, the obstacles inside the airspace. I will have a separate picture for that. These airspace may be reserved for the traffic that would be crossing your airspace from bottom to top, you know, so going from a lower level to higher level. Maybe there is an airport underneath here. And so this airspace, you yourself have to place some obstacles. So some obstacles are already given, you know, the weather systems or no-fly zones, but you should also give some holes, put some obstacles so that there is enough um, space for the air traffic to cross to and from different airports. More and more complicated questions that you have to answer when trying to estimate the capacity. Next thing is returning to the RNP requirement. Quite an important thing, which, well, not very recent, but still something which is still making its way into the air traffic management, is the so-called performance-based navigation, performance-based operation, or performance-based services. It's one of the pillars of the modernization of the air traffic system. And essentially it says that different users with different performance may get different services, performance-based services. In principle, the air traffic management, well, the whole air traffic system was kind of designed uh, having this paradigm one size fits all in mind. If you look at the airways, well, they were more or less for any kind of traffic. If you look at stars and seeds at the charts at the airports, again, it's assumed that any type of aircraft should follow the same routes. Sometimes you see these, I don't know, like in a Bromma chart, I saw a little arrow saying like slower traffic, keep right to get way for the bigger, faster guys. But in general, the predominant paradigm is that, well, we should have some kind of equity or equality, whatever that is. Everybody should get the same level of service. And that is being challenged if if somebody has invested into an aircraft with good navigational performance, installed a lot of GPS or whatever else on the aircraft. If it's a smaller aircraft, maybe it's a business jet, with the executive in the back seat who is willing to pay a lot for a good path, then why not? Similarly, if the aircraft is less noisy or has fewer emissions, why not giving the aircraft a better path? So what this picture shows is that, well, I was saying that the RNP is a fixed parameter and we are routing the air lanes of the fixed width. It's not true. You can route traffic with different RNPs, and if you have traffic with good performance, then it can squeeze through, the gaps between the weather systems through which kind of worse traffic or traffic with worse performance would not necessarily be able to go through. So we have to account for the performance, and we have to make sure that we are routing the maximum number of air lanes, again, taking into account the differences between the users. And the differences could be, as just described, in terms of the thickness of the air lane. We could also think that different, as already mentioned, different kinds of obstacles, well, may or may not be obstacles, may or may not be hazardous for different kinds of aircraft. For instance, larger aircraft could go through weather cells through which smaller aircraft wouldn't go. On the other hand, smaller aircraft may fly through noise-sensitive areas because they produce less noise. So what is an obstacle for one type of flow is not an obstacle for another type of flow. And well, these pictures, they can give a schematic representation of what we could have. So we could have hard and soft constraints, so shown by this different uh, shades of red. And well, everybody has to avoid the dark red, but this lighter red has to be avoided by darker blue, while the lighter blue can go through. And on the left here, you can route through, well, 4 air lanes, avoiding the hard constraints, but then you cannot route this more sensitive traffic, the dark blue flow. And well, if you route the air lanes as on the right picture, then, well, you can fit both the darker flow and the other one, the lighter flow, but yeah, with different trade-offs. So you can route different number of different kinds of traffic through the airspace. And all in all, what it teaches us is that, yeah, you can have different classes of traffic which have the demand for your airspace. And in this case, you know, the capacity of the airspace is not just the function of the airspace itself, and not even the function of the hazards or the obstacles that you have inside the airspace, but is also a function of demand. And this is the, again, the notion of this kind of demand-driven capacity, which in principle should be at the heart of the demand and capacity balancing. But the research is still ongoing on how to really define this demand-driven capacity, and in general how to do the demand and capacity balancing in the best, in the optimal way. Okay, so yet another turn of the page. We were talking about the obstacles as, you know, we knew where they are. They were deterministic. But of course, in reality, well, as Yolanda was also saying, we don't know the weather with certainty. And also the other kind of traffic, we don't know with certainty. There are delays and predictable delays and so on, lots and lots of stochasticity in the picture. And when dealing with the weather, what we have is we don't have these solid obstacles through which you really shouldn't fly. You have some kind of probabilistic forecast. And well, this map on the left is showing WAF, the weather avoidance field. It gives you the probabilities of having the hazardous weather at different parts of the airspace. And what you can do is you can say, well, wherever I have the probability above, let's say, 80% of there being a hazardous weather cell, I call it an obstacle. And then I'm just routing my flow through the deterministic weather systems like I have here on the picture on the right. So I'm just computing this min cut and so on. But there are other ways in which you can take the uncertainty into account. You can and actually have to somehow integrate the weather forecast from different services, from different kinds of the weather information. There is lots and lots of input indicators. You look at temperature, winds, yes, the cloud top, and lots of other input variables. And you're trying to understand, yes, the severity and the likelihood of a certain hazard. I don't go too much into the details here. It's still an ongoing research and probably will never end while the weather prediction improves. But all in all, we want to somehow integrate the forecasts on different time scales, providing the right kind of the forecast tailored to the ATM needs. So again, a schematic example, what we could have is something like this map of how severe the weather is at different parts. And then, as I said, you can model the severity of the impact as the weight of the path. And you would say that, well, when going through yellow or red zones, you kind of incurring a higher cost or higher weight of your path. And you can either go through a very thin part of yellow, as you have on the left picture, or you can go around red and yellow altogether with a longer path, but, well, kind of, don't want to say safer, but really having less weather impact, having less probability of being in turbulence or whatever that thing is. Next thing, when we, well, or in general, when we speak about probability or stochastic nature, we want to do contingency planning. We shouldn't just plan one route. We should think in terms of what if. And again, here, I'm showing just, again, a schematic picture. Let's say that this is an airport and you trying to route the traffic out and into the airport. And well, you know that it could be that this area is blocked by the weather. Maybe you have some kind of weather forecast. And you really should, when routing this route, the top route, you should think that, well, if the weather forecast is there, you should leave the room for the incoming route to go through. So you shouldn't route like this here on the bottom picture, so that when the weather system, the hazard materializes, this poor route would not be able to go around. So this kind of planning ahead and planning for the contingencies, you should kind of result to CDNR, conflict detection resolution, as well, there are several safety layers, but and CDNR is not necessarily the last safety layer. There is also TCAS, short-term collision avoidance systems. But anyway, already in the planning phase, even in strategic planning, you should kind of plan ahead and think of the contingencies, think of what can go wrong, so that you wouldn't have to invoke the CDNR and other things. Here is another example. Again, maybe red is the hazardous weather, and you don't want to route a stretch of a path like this between two hazardous weather systems that goes in between for too long. So there should always be this kind of escape routes. If the route is like this, then it's okay to. If the situation is like this, then it's okay to route the path over here on top like this, because, well, if there is some blockage, if the weather forecast is not precise, and actually this weather system is larger and this weather system is larger, then you can escape like this. Of course, this is quite a complicated weather system, and it's, again, not taken anywhere from reality. It's just an example, kind of an artificial one to show something. Again, yeah, to show the point. Again, we spoke about the taking into account the width of the air lanes that you're routing. And again, this is a picture that shows that depending on the width of the air lanes, depending on the performance, you can route the paths in different ways. Of course, contingency means giving the aircraft the possibility to maneuver if necessary. And yes, if you route the path again between two obstacles like this, then it's not too good. And what would be the right model of the path, which would tell you that that you shouldn't route something like this. You should be able to maneuver, and if your nominal path, like this blue path, becomes blocked, then you might want to have some wiggle room, some deviation paths, some alternative paths shown here with green. So instead of going by blue path, if blue path is blocked, you have some possibilities to go via green paths. And then again, you may draw quite a few green paths like I have on this picture. And then yet again, you may question yourself whether this is really a good set of alternative paths. And the problem here is that, well, okay, so you know that your blue path is blocked, and now you choose to, maybe go along another route, maybe something like this. Well, I guess that's not a route. Yeah, a route like this. But then maybe this route is blocked, and then instead of that, you want to go really to this route, or maybe go to this route. The problem is that these routes are topologically different. What it means is that you cannot kind of really go from one route to another without intersecting the obstacle, right? I mean, you cannot morph this route to this route or to this route. They belong to the so-called different homotopy classes. And two paths are in the same homotopy class if you can morph one path to another. So if one path is blocked, then you can change the path and go along another one, homotopically equivalent. Yeah, so if you cannot morph one path to another without jumping over obstacles, then maybe these are not good contingency paths. And then you start thinking about, well, just a single path. How good is it? How much possibilities does it offer in terms of contingency planning? Does it have a lot of wiggle room? We were talking about wiggle room, about attaching certain time stretch zones or holding patterns to the path. But those are fixed locations along the paths. In general, if you look at a single path, how much room does it have around itself where the aircraft could go if something goes wrong? And to estimate that, we were looking at the so-called Voronoi diagram of the obstacles. So again, as usual here, the red represent the obstacles, so the weather systems, And well, these dashed lines, they now don't represent the sector boundaries. They represent the Voron diagram of the medial axis. So what is that? It's kind of the lines that go as much in between the obstacles as possible. Or formally, if you look at any point on the medial axis, it is equidistant from two obstacles. So if you were to grow a circle on centered on any point along the medial axis, then the circle would touch two obstacles at the same time. So these medial axes, they're kind of as far from the obstacles as only possible. And where you have, like this vertex of the medial axis, you are touching three obstacles with the same radius circle. I don't think that this particular diagram is drawn very precisely, but anyway, the idea is that you're kind of trying to stay as far away as possible from the obstacles. That's something that is known as a Voron diagram or medial axis. And what you can do is you can create, yes, the medial axis of the weather systems, and then you can look at your path. And it turns out that you can morph your path onto a unique path in the medial axis. So there is one of the paths in the medial axis, which is homotopically equivalent to your green path, to a given path. So no, if you wanted to morph the green path to this path, well, you wouldn't be able to do it because it would have to intersect the obstacle, or you wouldn't be able to morph it, I don't know, to this path, again, because you would have to intersect the obstacle. But there always, it's a mathematical fact, there always exists a path in the Voronoi diagram, which has the same homotopy type as any given path. It's kind of the representative path. And so we can say that the wiggle room that our original path has is the same as the wiggle room that the path in the Voronoi diagram has, because any path with the same homotopy type, like maybe this path, well, and this path, and both green paths, they have the same wiggle room. They can wiggle around in the same way between the obstacles because they have the same homotopy type. That's the definition of the homotopy type. So we can look at this representative path in the Voronoi diagram. And then, well, we know that there is on any point of this path, there is a circle which touches at least two obstacles. And you can wiggle within these circles because these circles are obstacle free. So you can actually put these maximal disks, yeah, these purple disks centered on the path in the Voronoi diagram, and this purple region, what you see purple now, is something that defines the wiggle room for our route. Okay, so maybe somewhat complicated, but still nevertheless a construction that you can do step by step and define the wiggle room. And then of course you can recall this idea that you should well, do all the operations and all the wiggling within a sector. And well, now the dashed lines represent some kind of a sector. So you would cut the purple to stay within a single sector, and again, give you the wiggle room inside a sector. Okay, so that was yet another way to model paths. And our colleagues from, while we were working with Metron Aviation quite a lot, and they were saying that, well, these are still research questions. It's not really how the controllers do things these days, but nevertheless, these are all good questions. What are the right models for the flight paths to represent the actual paths, how the pilots fly or can fly their aircraft? And then when we know what the right model of the path is, then we can ask ourselves how many paths we can route and get one of the answers to the question of what the capacity of the airspace is. And as I've heard from Eulalia, well, that's not a question which is answered with certainty yet. It's being reevaluated. And what I've been talking about and what I will continue talking about is this capacity not related to the complexity of the traffic, so kind of human factor taken out of the picture. Just assuming that controllers are really good, they can handle any amount of air traffic. And in fact, here again, we are talking about very structured flow, about the flow going along the air lanes. So, well, it may not be too hard for the controllers to control it after all. Okay, lifting other assumptions. So we were talking about, the two-dimensional questions. Going to the full 3D may be complicated, but we can kind of go into 2.5Ds and think of, two kinds of airspaces. So there is one flat airspace and one airspace which is a transition airspace where the aircraft go from the airport and to the airport, and they intersect. They have common obstacles. How do you route the air lanes through these two airspaces? Well, that's not an answer to question. We don't have the answer to it. These poke-throughs I was already mentioning. Yes, for the aircraft to change altitude and go through your airspace, you would have to put in some obstacles in the already weather-impacted airspace and still route around existing obstacles and the obstacles that you put in. Again, a non-answered questions. Yes, flying over the ecotops. I was talking about that. Well, you can consider the two air spaces on the adjacent flight levels, and some of the obstacles are common, but some of the obstacles are only for the lower airspace of for the lower flight level. Then yes, how do you route these routes on two different levels, flight levels? Again, what's the capacity of these two levels, and so on and so forth. Yet another important direction is to take the time into the consideration. The obstacles, in particular the weather systems, are moving, and if they move from some position to another position, then well, maybe only few of your air lanes stay and can remain obstacle free for some time horizon. Well, here is some example of weather systems going through, and what you may want to do is you may want to try to morph your air lanes so that they go around the obstacles in different ways. And if you change your air lanes, then the capacity for the dynamic air lanes may be larger than the capacity for the static air lanes. So in the most general case, you can represent, the aircraft you can represent with a disk, which represents the protected airspace zone around the aircraft, well, few nautical miles, or whatever that is, and then view the trajectories really as these tubes in space-time. So here on the right, you can see these tubes. Each of them represents a trajectory, and you want to pack as many tubes as you can through the XYT, taking the time component into account. And here I'm showing something from a video that we produced. I don't want to show. So yes, I didn't want to show the video inside the class video, but you can watch this video at another time and see how we were finding quite a few paths through a weather impacted airspace. But what I did want to speak about are the routing paradigms. Well, as we were talking about these static air lanes, when the weather systems move, if they intersect the air lane, then the air lane would be closed or would be non-existent. You could have something which is called free flight. There are no air lanes. The aircraft are just disks, and you want to make sure that these disks remain separated and from each other, and also from the weather systems, even when the weather systems start moving. Or you can have these flexible flow corridors, or well, we call them morphing noodles, that would morph as the weather systems move. And depending on the three routing paradigms, you can have different kind of traffic. So these are short videos, these are 30-second videos, and I will show them inside the recorded Zoom lecture. That previous video that I didn't show was like 8 minutes long. So here again, you see the Cleveland Center with the blue, yes, the Great Lakes, or some of them. And now it's a real weather. So we took, I think, half an hour of real weather, and we were routing the air lanes. And these air lanes were static, so the weather systems would move. And we wanted the air lanes to stay clear of the weather through the whole half an hour. And well, we were able to route 4 air lanes, and in principle, well, route quite a lot of air traffic through it if you want to route the air traffic really ducks in a row to the maximum capacity. And then we looked at the same instance. So the weather system was the same, and we were routing the free flight. So now no tubes, no corridors, no air lanes, no whatever. Everybody just flies through. And you see we can route much more. Of course, this would be an air traffic nightmare, monitoring something like this. So maybe we could look, and we actually did look into something in between. So as I was saying, these morphine noodles or whatever you want to call them. So these are again the air lanes that, well, the aircraft would follow one another, but they morph. As the weather systems change, they start morphing. And you can see we can route more. We can route 6 of these air lanes through, and it's quite a structured traffic. Even though they morph, still the aircraft follow each other ducks in a row, and the controllers would be able to say, stay north of this constraint, south of this hazardous weather, and so on. So maybe these morphinules, they provide more capacity, but well, the traffic is still structured, so maybe not as bad as, well, the free flight. Okay, so we were talking about contingency, we were talking about well, the temporal component. Of course, we can start looking at 2 things at a time. So yeah, we can look at the flow, how it looks in the this time a one-dimensional case. So we're not looking at x, y, t, we're just looking at the xt plane. So all these aircraft just follow a single line. Each of aircraft starts at different times and goes along the same line. And then maybe again you have this aircraft with dysfunctional transponder, and it well, it is observed somewhere at this time, and it goes with certain speed. So at another time it can be somewhere else at a larger area. So in xt space you would have to avoid this obstacle, which is the obstacle in xt, and yeah, modify your aircraft paths. So some of the aircraft would have to speed up, have to go faster. Some of them would have to hold. Some of them would have to slow down and avoid this obstacle in xt. And you can similarly do in XYT again. So there are a few aircraft, and then maybe there is some, unavailable airspace, some cylinder, and you want to go around this obstacle with your paths. Okay, I did have a full section in this lecture, in the capacity estimation lecture, devoted to capacity in CES, Single European Sky, and CESAR, Single European Sky ATM research. But I watched the lectures that Eulalia gave, and I think she gave quite a good exposure to the capacity in CESAR. You did look at these KPAs in ICAO and the CESAR or CES key performance area. Well, I have these 4, which used to be in the first edition, I guess, and also in the second edition. Anyway, earlier in the master plan, and then you looked at the 6 in the newer master plan. Yeah, so these are some numbers from the older goals that CESAR had. Again, I guess you looked through them in quite details. Yeah, this 3-fold increase of capacity that they wanted to achieve. Yeah, these are the other KPIs. So I guess I will not stop on them. I will use this picture later to kind of show you how to measure the capacity in what units, but will not stop on this. I guess you You've been through that. And so now, yeah, I just give you some quotes from the master plan. Uh, well, with the different economic situation that we have now and had, well, also before the economical crisis, well, the capacity may not be necessarily the highest priority. So earlier, the scenarios were driven only by the capacity, but now with the economic situation, people also look at other things. One quotation that I found in now I don't have the edition of the, I think it was the second edition of the master plan, and maybe it still sits in other editions. But anyway, looking at the different key performance area, it says that environment, cost efficiency, and safety are expressed in qualitative terms, meaning that capacity is more quantitative, or maybe even most quantitative out of the KPIs. Okay, so how do we measure capacity if it is so measurable, so quantitative? Well, you look at the performance scheme, and you can find things like that. Increasing capacity means reducing air traffic flow management delay. And again, Eulalia spoke to you about the difference between ATFM and air traffic flow and capacity management. But anyway, so according to the performance scheme, capacity is somehow related to delay per flight. Again, delay attributed to air traffic management, air traffic flow and capacity management, or air traffic flow management. So capacity is somehow related, some function of delay per flight, at least judging from this. Well, in another place, we actually speaking about the capacity needs and have this table, which basically says that, well, the capacity needs can be, well, low or very high. And in the airport or TMA areas, even smaller number of movements per hour defines higher capacity needs than in en route. So kind of en route is easier to handle. Well, that's understandable. In TMA, you also have the vertical component. But what's interesting is that here they speak about the capacity needs. And this is, again, somehow the need is the demand, right? So that's how much traffic wants to fly through your airspace. So maybe that also brings you back to the demand-driven capacity, which we still don't know how to express and measure. Other things. So again, in the same master plan, they speak about capacity, how it increases as a function of workload per flight. While workload, they speak about the controller's workload. So this is maybe this human-induced capacity. Earlier, they were speaking about the delay per flight. Now it's workload per flight. And it's a separate, super complicated question, how to measure the workload. You have to measure the complexity of the traffic. You may use it as proxy to the workload. Anyway, very complicated. You look at papers devoted to capacity, and within a single paragraph, you can see that the capacity is the number of aircraft. Well, they didn't take the English lesson with us, so they don't know that the plural of aircraft is aircraft. But anyway, they say that the capacity is expressed as a number. And then, well, in the same paragraph, they say that the capacity is this map value, and map is this monitor alert parameter value. So Eulalia was talking about also these nominal capacities of sectors. And yes, for the sectors, there are these monitor alert parameters. If there is too much traffic through, then the controllers should be alerted that, well, the capacity is nearing its limit. But anyway, so they say that this map value is estimated as a function of the average dwelling time, how long the aircraft spend within the airspace. Well, it's not exactly equal to it. It's like 1.6, the average dwell time. But anyway, the capacity, we're not even talking about the definition of capacity. We're just trying to understand what are the units of measurements. And it can be just a number, or it can be a minute. And again, in the same paragraph, they cite another source that defines the capacity as the maximum allowed aircraft. But again, the aircraft count, again, coming back to defining the capacity as a number. So is it defined in numbers? Is it defined in minutes? Is it defined in some other ways. And here again, I'm showing the part of the master plan and some of these key performance areas where they express the capacity both in terms of the minutes, well, of the delay per departure, well, per flight if you want, and also in terms of the number of aircraft. So, well, go figure out what is the one and only definition of capacity. Maybe there is none. And I've been collecting over time different well, not just definitions of capacity, but even just definitions of units of capacity. Often they say that it's number aircraft per unit of time, like per hour, per something that can be, again, handled by controllers. So that's human-induced capacity. But again, now it's measured in minutes in minus first, 1/minutes. So even just the units of measurements are not set for the capacity. There was in 2017 a very interesting document came out. So Yulala was talking about different, well, waves or whatever they called, phases of Cesar. I don't mean this deployment and other phases, but that, well, there was Cesar in 2004 or CES in 2004 and then 2009 and so on. Now it's Cesar 2020. Anyway, I'm not sure what the political currents underneath, but at some point, the European Court of Auditors had a special report looking at CES and in particular at Cesar, with quite a lot of criticism, which I actually find sometimes grounded, sometimes just interesting to look at. So I'm not going to go into this report. It's an interesting document by itself. But then the Commission, of course, replied to the report. And one of the things that was criticized is that, well, the question of the capacity, the ambitious goals weren't reached. And they said, well, the Commission wants to clarify that there is no specific indicator to measure capacity. Okay, we admitted that, but it's constantly monitored, changed, and there is a research going on, and so on. So there is a lot in this special report. They kind of complaining that research is open-ended, well, as if the research was closed-ended ever. But they also have quite a few, well, a lot of really good points. And one of the points, which of course is quite relevant now, not only in terms of the capacity, but in general, it said that Cesar was trying to reach certain targets expressed as numbers, as certain quantitative targets. And they said that it may not necessarily be a good idea to try to reach them since the situation changes. And actually, we are following up on this quite actively. We have this full project currently running together with LFV. It's called TMA KPIs, towards multidimensional adaptive KPIs. And we are trying to say that when you assess the performance of a system, in this case of air traffic management system, you shouldn't just try to say, well, certain numbers, certain KPIs have such and such values. You have to assess it in comparison to what is possible, what is optimal under the current situations. So this is where we have all our optimization algorithms and all the optimization that you study in this course. I mean, we are not the only ones trying to optimize air traffic management, obviously. So what we're trying to say is that under the current circumstance, under the given circumstances, given weather, given, I don't know, other things, political situation, well, pandemic for a second, what could have been the best performance? We solve the optimization problem, we show what it is, the performance, the best performance is, and then we compare and see how the system performs in comparison to this indicator, not in comparison to 2004, 2012, or whatever Cesar was setting as their targets, but really doing that. And I have a lot of elevator pitch slides which really speak to people. Sometimes you want to decrease communication overhead between controllers in the adjacent sectors. But then let's say there are political tensions between countries, and they don't fly from one country to another. There is no air traffic between Russia and Ukraine. Then, yeah, there are other situations when, well, the traffic goes to zero, the communication overhead goes to zero. But this is not due to good research or technology or anything. It's kind of for free. And this is what the European Court of Auditors says about, even though not giving specific examples, saying that, well, certain indicators become just unreachable, and we shouldn't blame the air traffic management for that. And certain indicators are kind of reached for free, and then we shouldn't praise the air traffic management for that. So quite an interesting document. If you are interested in these things, you can read it. But anyway, yes, the Commission admitted that there is no specific definition of capacity. And just to summarize what I've been talking about in this lecture is that well, maybe our understanding is that the capacity is not just a function of the airspace or of the weather or of other things. Different routing paradigms, they give rise to different capacity, but also different complexity of traffic. And our research, well, we are just trying to help in quantifying the trade-offs and define the operational requirements, the performance requirements that would lead to different levels of capacity. Of course, it's important to take into account the temporal component, to plan ahead, to go to three-dimensional trajectory or to the 4D trajectory, to these trajectory-based operations that Eulalia also mentioned. So yes, very much in line with what Cesar is doing. Surprise, surprise. Yes, we want to estimate capacity in different ways and estimate it well. Right, so, and Cesar, yes, the solution is to use, well, not one of these concrete solutions, but the general idea is to go to four-dimensional trajectory, to trajectory-based operations, to performance-based operations, and of course have the flexible use of airspace. Again, you heard about that from Eulalia. So yes, the capacity estimation evolution is maybe not a linear thing. There are quite a few branchings, and I'll just want to finish with something that could be a most general model, but this is really like I'm throwing in a few thoughts, and it's not only my thoughts, and in general, some research ideas that, well, we were talking about input and output and optimization problems, so we can have some region of interest, some airspace, which could be 2D or subset of 3D. We have some time horizon, we can have some sliding window when the information updates every time. We can have the demand. We were talking about the demand-driven capacity trajectories that, well, may be stochastic, may have some distribution of the entry time given by this estimated time of arrival, and so on. The equipage class, which is specified, we were talking about different classes of traffic that goes to the airspace, the points of entry and exits, and so on and so forth. And then, of course, if this information is too fine-grained, then we can try to cluster the trajectories, somehow to bucket them or whatever you want to call them, and try to route, well, thicker path, where thickness now is not only in terms of this RNP width, but a kind of thick flow going from one side to another, also within a certain time window. Yes, we have to take into account weather events, different types of weather events, understand their different kinds of impact on the on the traffic. Look at XYT space. Here's a picture of that, and design these tubes that should be flexible. Well, in general, because of the flexible use of airspace, but also because they can really morph, as we saw. They should be dynamically designed and changed as necessary. And in the output, we would have capacity. We have to understand what the capacity is. Is it monitor alert parameter with the human factor? Is it demand driven, and so on and so forth? We have this basic model with the west to east, mostly I would say suited to the American traffic, where there is indeed a lot of west to east or north to south traffic. And there is a link to flow-based route planner, which was done by my colleague. I'm not going to link to that, but there is a short movie on how it works. But in EU, a lot of traffic is just crossing. So the airdromes are all over the place. And there is some work that extracts dominant flows over Europe, so they certainly exist, but still, you cannot just say that mostly people fly west to east or north to north to south. There is also these economic questions, especially in EU, with the route charges that the airlines pay when overflying flight information regions of different countries. And I will be talking about the economic mechanisms in the next lecture. Yeah, here are just some examples, some output videos of how this traffic could be deconflicted by using various kinds of algorithms. I will not go into the details. And last but not least, so I was mostly talking about the en route airspace, but I want to spend a few last minutes describing the super dense operations, as they call, but well, super dense meaning that the highest density of traffic is in the vicinity of the airports. What can we say? Which of the theory transforms to the operations in the vicinity of airports and which doesn't? And again, when just few slides, I will not stop too deeply on them, but looking at where you have most incidents, manually reported versus the kind of real ones. And you see that there is, well, quite a few incidents that happen in the vicinity of the airports. Anyway, back to our models. So the airspace, well, it could be en route, or as on this right picture, it could be terminal airspace, again, weather impacted, and you want to route the traffic from, well, this circle, which represents the boundary of the terminal airspace, down to the airport. And yeah, you have to avoid hazardous weather cells, and you looked at the problem of locating these fixes, metering fixes around the boundary of the airspace. Again, the airspace may be weather impacted. How do you route? What's the capacity of the terminal airspace? So yeah, you also have your region of interest in the en route, but you can also have sources and sinks inside the region, modeling the aerodromes. And yeah, they may be weather impacted with different types of constraints. And yes, you may want to ask a question of how much traffic you can route from the outside to the inner rim. One thing that one may bear in mind is that you often have this metroplexes when several airports are in the vicinity. So this is the New York area with LaGuardia and JFK. Uh, I guess also, yes. So there's also New Jersey. So Newark is also in there. But actually in Paris and even in Stockholm, we also have Arlanda and Bromma, which do constitute a metroplex. So there are a few things where the traffic interacts, few places where traffic from Arlanda and Bromma traffic interact with each other. And yes, we were talking about this contingency planning and wiggle room in en route airspace. Same things go for the airspace, for the terminal airspace, for the merging route. You need holding in the terminal airspace more than anywhere else. And yeah, you may think of how do you attach these race tracks for holding for your aircraft. Yeah, these all operational flexibility and mitigation strategy, how much flexibility, how much wiggle room the routes have. You can also define them for the merging routes. Yeah, so here is the picture. One thing which is particularly nice about air traffic is that actually the picture is not fully three-dimensional. Come to think of it, the aircraft have certain descent profiles. And if you take such a descent profile and start rotating it around the z-axis, then you would really have this conical surface, and it's a two-dimensional manifold. It's in 3D, but still it's just a surface. So some theory and algorithms and applications that we have for our air traffic en route in the XY may still translate to estimate the capacity in the terminal airspace. So here's this example of the manifold. Yes, it's a three-dimensional thing, but you're really looking at the two-dimensional surface of it, two-dimensional manifold. And the weather systems, they just do some obstacles, some poke throughs. So yeah, as en route. Yes, so you look at the weather system, and again you can define the same kind of graphs in which you search for the path. Well, we were looking for the path from source to sink from left to right. Now this is our source and this is our sink, and we still can define the capacity and use the min cut for a given thickness of lanes and so on. So yeah, some of the theory translates also into the TMAs. Yeah, so this is the just a recap of what we had back for the end rotator space. You can also try to define yeah, these fan out trees and fan in trees for the arrival and so on. We do have quite a lot of projects that are related to TMA and routing in TMA. Not so much estimating the capacity, but nevertheless doing the routing. And here are just a couple of yeah, links to videos. Again, they are pretty short. You can see how the traffic flows may be managed in the TMA. And the last but not least, I want to finish with this slide. Well, kind of reminding and bringing your attention to this wonderful new things called continuous descent operations, CDO. And again, I know that Eulalia mentioned that the idea is that, yes, you would kind of glide with idle thrust or whatever that is, with minimum thrust, instead of doing this nominal approach, and then you will be higher than the usual approach, the stepwise approach. So you will decrease the noise, and you will also decrease the CO and other emissions. So we are actively working, and not only us, a lot of people are actively working on the continuous descent operations. There is a special task force in Eurocontrol, and a lot of our colleagues from LFV are part of that task force. We are doing algorithms for continuous descent. Yeah, so maybe if you're looking at the optimization problems in some of the recent conferences, you may find some of them that we did, in particular on continuous descent. Little warning, these are not the simplest optimization problems. So, well, if you like them, you can certainly look at them. And that's it. That's the end of the lecture on capacity estimation.